Good morning and welcome to a geometry video of guided notes. We'll look at the text together today and highlight some of the important takeaways. Today's topic begins with volume. And what is that? Scrolling text, I don't know, it must be a distraction. Try to ignore it. Anyways, volume of prisms and cylinders, and then later we'll get to pyramids and cones. Let me start by addressing what we've done previously. We talked about area, right? The measurement of amount of space a flat thing takes up, how much carpeting, right, covering the wall in paint. Now we want to fill. That was two-dimensional. Now we're going three-dimensional with volume. Three-dimensional measure of space. Length, width, height, depth, thickness. Any word you want to use, you're going to need three words now. Dimensions. So all of that stuff about area is going to carry forward, and it's the same concept. It's just, it's one more dimension. Okay. Take a look at the volume formula. How do you generate volume formula? Well, looking at a stack of blocks, so that we have each individual unit outlined and clearly labeled for us. We have one block down here, and then all the way back makes 4. And so that row of 4 is then multiplied by this width here 2, so that we know secretly behind here there is, right, a total of 8 blocks in that layer, as it were. And then what we're going to do is we're going to stack up the next layer on top of layer. And so we have 2 times 4 blocks sitting there, stacked 3 layers high. So the first layer, 2 times 4, has an area of 8. Depends. Right, the area is 8. This is centimeters times centimeters, so it would be centimeters squared. But now we have 3 stacks of 8. So we're going to multiply yet again. Get the volume. 3 times 8 gives us 24. Carry the units over. I now multiplied centimeters squared times another centimeters, so that gets centimeters cubed. And you can do the same thing for larger and bigger. There's just more squares involved. So notice what we've done is we have taken the area of one base, one face, right? We've multiplied that by how many layers of that face we have. Actually, I could go back. Let's look at it a different way. I could instead look at this face of my rectangular prism as the base, as it were. In that case, the area would be 2 times 3. That would be 6. Then the question is, how many layers of 6 do we have? In this case, going back in that direction, I have 1, 2, 3, 4. 6 times 4 is 24 again. Works either way. So it doesn't matter how you label everything. It all comes down to take an area, which you already know how to do, multiply by 1 more. So for their rectangular prism volume conjecture, if B is the area of the base and H is the height, the volume is going to be, that's right, base, capital B, times the height. So really we've said the same thing as we did for two-dimensional rectangles, except now when we say base, we mean a area already. So this is already a little b times a little h. Keep that in mind. Area of the base. And we could keep going with a triangular prism. It works the exact same way. Nothing has changed here. We're still going to look at this base here. In this case, it's a triangle. Okay, so you use a different formula to get the area of that base. But it's still, to fill the volume, you have to take triangle on top of triangle on top of triangle on top of triangle, all the way up. We want to know how many layers does it take to fill the dimensional space. So once again, if B is the area of the base and H is the height of the solid, then the volume is still area of the base times height B. All right, moving on. Let's ask a more interesting question. What about oblique prism? What happens if, for some reason, say an earthquake strikes and all your papers get shoved over and are crooked? What do you do then? Well, think about these two stacks of paper. Right? Is there any difference in the number of pieces of paper just because you shoved it over, made it crooked, or go the opposite way if you take a crooked stack of papers and straighten them up so they're nice and clean and perfectly rectangular box there? No, there isn't. You didn't change the number of pieces of paper. You didn't change the mass. You didn't take some away. Right? It's all still there, and each piece of paper takes up the same amount of space. So altogether, they should take up the same amount of space. That's all volume is. Which means, yet again, we still want to multiply a base times a height. Except in this case, our height is a little. Notice that 6-inch height there. Right? That is a perpendicular, see the right angle, perpendicular height. If you look at this object from the side, you will notice, once again, it's a parallelogram. Remember, in area, the area of a parallelogram was the same as the area of a rectangle. So again, we're still taking that perpendicular height to multiply by. We're not looking for what is the length along that diagonal side. We don't care about that on the diagonal day. Okay. Here's another example. Moving on to cylinders. They're just like prisms, except the base is round. Okay? Stack of crackers. If I tilt my stack of crackers, did the number of crackers change? No, clearly not. The crackers still take up the same amount of space individually. So adding together, what is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 crackers? All 10 crackers still take up all the same volume together, no matter how you've arranged them. So then, for an oblique prism or cylinder, the volume should be the same as the right prism, right? Volume of an oblique prism is the same as the volume of a right prism that has the same, well, it's got to be all the same properties. What are those two properties that contribute to the volume? That's right. Capital B, capital H. Same, let's see, grammatically it would make sense to call this base area height. There we go. And then finally, they go ahead and put it all together. The volume of a prism or a cylinder, doesn't matter, right, oblique, same difference. Every time is, we're just gonna copy those there. Same things once again. Base area multiplied by the height. Or you could say area of the base if you like to use extra ofs. That's really about all there is to it. Again, expanding area, these same ideas into the third dimension. Okay, let's do an example together. Here, so we can go ahead and do it ourselves. Find the volume of a right trapezoid prism that has a height of 10. Two bases of the trapezoid measure 4 centimeters and 8 centimeters, and its height is 5 centimeters. Okay, lots of information there. We want to find the volume. It is some kind of prism, so we're going to take area of the base multiplied by height. Tell us the height. We just need to find base. Area of the base. What kind of prism? That's where you need to know the rest of geometry from before. What shape am I dealing with? In this case, we're dealing with a trapezoid. So I need to recall the area of a trapezoid formula, which was little h, height, times the average of the two bases of that. B1 plus B2. So let's take a look. The two bases of the trapezoid measure 4, 8, and its height is 5. There is the picture there as well. Let me go ahead and highlight this for you. Right, here is our trapezoid that we are concentrating on. Got 8 down there, and this 4. Copy that guy over. Same as the 4 on the front face trapezoid we're using. And its perpendicular height, they tell us, stretched over here is 5. So let's put all of those numbers together. And in fact, do I need to know, do I actually want a number for the area of the base trapezoid? Do I ever need that in this problem? Is there a part 2 where that part might be useful? No, not really. So I'm going to cut to the chase. I'm going to stick all of these letters together, one big equation, one calculation. So the total volume is going to be, replace capital B with all of these numbers. Little h, that height of the trapezoid was 5. Little b1, 4, plus little b2, 8, divide by 2. And now times the great big height of the whole prism. That was... Alright, and then again, you can whip out your calculator if you'd like to. I'm going to do a little mental math real quick here. 8, 9, 10, 11, 12. Divided by 2 is 6. Okay, so that's 6. 6 times 5 I know is 30. Times 10, just slap another 0 on the end. So we get 300. Check our units. Everything was in centimeters. Centimeter, 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 centimeter. Yes. Good. No sloppy unit conversions. All centimeters cubed. Okay. Volume. We are. Check back with the text to see same number they got. It is 300 centimeters cubed. Nicely done. Notice they use the 1/2 multiply. I did the divide by 2. Doesn't make a difference. Okay. Now, moving on. What about those fancy pyramids? And of course, their rounded partners, the cones. The volume of a pyramid and a cone. How are these different? Take a look at the comparison here. I've got the same bases. I've got the same heights. But do you think they're going to be the same volume? Clearly, they are not. Let me draw on top of the pyramid here. If it was a prism, all of these edges would extend up, right? Up to here. And we would have all of this extra space to fill in. But now we don't. So it definitely needs to be smaller. Okay? Remember your area problems. If we had a parallelogram, rectangle, doesn't matter, and we want to divide that down into a triangle, the triangle has the same base length, the same height there. Let me, which colors make that? Right? Height and base. Perpendicular measurements. But the triangle didn't fill up the same space for the exact same reasons. It's missing kind of those corners, if you will. We had to lop those off. Area, if you recall, the triangle turned out to be 1/2 of the area. Is it going to be a similar fraction for volume? The answer is yes and no. Yes, we do want to multiply by a fraction. No, it's not going to be 1/2. I can get into a whole another video on exactly why it is the fraction that it is, but let me give you a more convenient thought. How many dimensions is the triangle and parallelogram? 2 dimensions, they're flat. And in 2 dimensions, we multiply the triangle by 1/2 area, 1/2. I'm going with this. How about the pyramid? The pyramid exists in 3-dimensional space. 3 dimensions. So we have 3 different directions in which to decrease the volume that we didn't take up by the prism. So instead of 1/2, we're going to multiply by 1/3. 1/3. Triangle is in 2 dimensions. Multiply by 1/2. Pyramid is in 3 dimensions. Multiply by 1/3. Again, that's not a great explanation for why it works, but it is a good mnemonic for remembering what that fraction is. Because otherwise, the formula is going to be exactly the same. So for our pyramid cone volume conjecture, once again, B is the area of the base, H is the height, so our volume is going to be that B times H, you're using capital letters this time to distinguish, times 1/3. Or divide the whole thing by 3. That is our new volume formula for pyramid or cone. Anytime it all comes down to one point up. And that's pretty much it. We can go ahead and do an example. We've got, the book has a little more complicated one of a hexagonal pyramid. You are welcome to work through that one on your own. But I'm going to do this one down here, circular base cone, just to remind us how circular bases work. So this cone has a base radius, 3 inches. Okay, you can see that marked there in the diagram. And a volume of 24 pi inches cubed. Find the height. Ah, this is one of those working backwards, guys. Okay, so let me mark in the diagram itself what we're looking for here. We're looking for that height right there. We know the volume. We're also dealing with a cone, so the volume formula that I want to focus on is 1/3 times area of the base times the height. Now, except this case, I'm looking to solve for that height. So let's do a little bit of algebra manipulation right now before we make things more complicated. Isolate the variable that we are looking for. So I'm going to divide both sides by b equals 1/3 h, and I'm also going to multiply both sides by 3. Okay, kind of went ahead and I combined those steps there. Right. But I hope you can work out why this equation is just as correct as the other. So I need to find v and b. What else we got? We know v. They tell us the volume is 24 pi inches. What I don't have is b, the area of the base. So I need to find that one first. What shape is my base? It's a cone, so the base is a circle. Area formula for a circle is, right, pi times the radius squared. Pi r squared. Ridiculous. Everybody knows you bake pi, it comes pi r round. Square. Square is a cobbler. So anyways, base pi r squared. And they tell us what my r is, that small radius, 3 inches. So now let's go ahead and fill in all of the numbers I have. We've got the 3 times b, 24 pi, divided by b, which is another pi times r squared. My r is 3 squared. That is going to give me h. I have everything I need. Notice I have a pi on top, pi on the bottom. Don't have to worry about that intermediate decimal. If we're left with a pi, don't worry, approximate it. It is about 3.14. That's good enough for our purposes. I like including more whenever possible, just or that rounding error issue. If you truncate it too soon, or just use the pi button on a calculator. Pretty much they all have them now. But we don't have to worry about that. We just have pi eliminated there, 24 up top, 3 squared on the bottom. We got a 3 up here. So this 3 is going to reduce with one of those 3's. Crossed out the squared there. Remember that this 3 squared actually means 3 times. That is the thing that got eliminated, not the 2 power squared, because it was representing the denominator. And now we just have the only thing left, looks like 24 divided by 3. And our multiplication table locked in our heads says that must be 8 will be our height. What were the units? Everything here looks measured in inches to me. So our height will be in inches. Of course, run a full dimensional analysis on that if we wanted to, just to be sure, but it all works out. The only inches left. So 8 inches. Be sure to include the unit. Okay, the units are important. We are dealing with actual objects, real measurements here. And that's going to do it. There is volume of prisms, cylinders, pyramids, and cones. That's 4 whole shapes using really only 2 equations. Not so bad. Not a whole lot to remember. Okay, I then leave it to you, your turn. Why don't you try the problem below, see what you can do about finding the volume of this square pyramid. And for argument's sake, let's say the units here are in centimeters. All of those are centimeters. So be careful what units you'll have for your answer. And that's going to do it for today. We've covered volume of 4 different shapes, 2 different formulas. There's some other activity for you over there. I'll leave you to figure that one out. But for now, I'm going to call it the end of the video. Thank you so much for watching. So long, farewell, enjoy the rest of your day.